Hello and welcome to the final live session of JuliaCon 2022. It's been an exciting couple of days. My name is Valentin Shuravi. I'm one of the general chairs of the conference, and it is my privilege to introduce our last keynote speaker, Husain Attarwala. Husain is a clinical pharmacologist. He's a researcher in drug development. Currently, he's serving as head of clinical pharmacology and pharmacometrics at Moderna, and his research focuses on developing predictive models to guide clinical dose decisions for mRNA vaccines and therapeutics. And Husain, at this, I hand it over to you.
Hi, yes. Sound check. Can you guys hear me okay?
Yep, we can hear you.
Yes, okay, awesome. Okay, and the slides are visible?
Yep.
Okay, thanks. So thank you to all the organizers for inviting me here for this talk. It's a pleasure to be here and share some of the really cool things that we're doing here at Moderna to support development of our vaccines and therapeutics using modeling and simulation. So these are some forward-looking statements that we are going to make and disclaimers. So jumping in, so what my role here is at Moderna is that I head up the clinical pharmacology and pharmacometrics department here. So we do model-informed drug development using modeling and simulation. So what is pharmacometrics? For those who are not familiar, pharmacometrics is the science of interpreting and describing pharmacology in a quantitative fashion. So by pharmacology, we mainly look into pharmacokinetics and pharmacodynamics. Pharmacokinetics is the mathematical understanding of rate of absorption, distribution, metabolism, elimination of the drug and its metabolites. In simple words, what body does to the drug is PK. Pharmacodynamics, as you will hear more and more in the talk, is the study of kinetics of pharmacological response at different drug dose or concentration. In other words, once the drug is in the body, what are the effects of the drug on the body and how long do they last? What is the relationship between dose, concentration, etc. is pharmacodynamics. Looking at it visually, so once a drug is administered, it gets absorbed, distributed, metabolized, and eliminated from the body. When we collect blood samples at various time points, we see that concentrations rise initially as it is absorbed, reaches a peak, and then disappears from circulation over time as it is distributed or eliminated. The concentration at various sites in the body leads to effect and the relationship between the effect and concentration is called pharmacodynamics. Now, once we combine PK and PD, we get a PK-PD relationship where you can see effect versus time, and the mathematical understanding of these kinetics and dynamics over time course is what we describe using different models in using ordinal differential equations and whatnot in pharmacometrics. Yeah. So why is it important? So pharmacometrics plays an important role at various stages of drug development. During early phases, modeling and simulation helps in guiding dose selection for first-in-human studies. In phase 1 clinical study, pharmacometrics helps in understanding dose response, exposure response, and exposure safety relationships, which helps in predicting dose levels for later phase studies. At the end of phase 1 or phase 2 studies, modeling and simulation plays a very important role in selection of phase 3 dose. It is important as safety and efficacy are linked to dose and exposure. And as you can imagine, if the dose is too high, it may show unintended adverse events. And if it is too low, it can lead to suboptimal efficacy. And indeed, selection of the wrong dose is one of the very topmost reason of why many drugs fail in phase 3 studies. Using modeling and simulation, we really get help in predicting safety and efficacy outcomes using prior data while going through various learn, confirm, and predict cycles. Uh, so once we have selected a phase 3 dose, we have conducted a phase 3 trial. Then at the end of phase 3, again modeling and simulation plays a very important role in understanding covariate effects, dose, exposure, safety relationships, and what kind of dose and um, needs to be taken for different subpopulations, and that ends up on the drug label, which is uh, on the drug label, approved drug label. The dose that you see is backed by a lot of actual data and the modeling and simulation that has been done to support it. So in our talk today, I will walk you through 3 examples where we have utilized modeling and simulation to guide dose optimization at various stages in drug development. And before we jump into our examples, let's briefly look at the workflow and tools we use to achieve our modeling and simulation objectives. So to achieve what we saw in the previous slide, as you can see that it spans across the development life cycle of a drug from early stages, preclinical to clinic, to all the way to approval and post-approval. In general, there are a lot of different tools that are available and used to do this kind of analysis. So those include like NCA, non-compartmental analysis, population PK/PD analysis, PBPK models, QSP models. I will not go through in detail of what all of these are, but to enable dynamic drug development, and go through multiple cycles of model creation, validation, iterative simulations. We need tools that could enable that. And there are like variety of tools available, but there is not like one tool that can do most of it or all of it. The Puma's software within the Julia ecosystem provides a one-stop for all sorts of pharmacometric analysis and helps in accelerating model development and simulation workflows. And it was important for us to have such an innovative tool to keep up with the pace and the speed that we entered into and execute those workflows. And as you can see, the statement from FDA, which says that model-informed drug development approaches are extremely important for maximizing the probability of success across different clinical studies. And there are a lot of examples where these approaches have become very useful and changed the course of drug development into success. Yeah. So to have a tool that is acceptable by regulatory agencies, those tools needs to be robust, validated, reproducible, and need to deliver results in time such that we can make those decisions when the need is to be made. So after rigorous testing and validation, we engaged Pumas to tailor all our modeling and simulation needs for the MIDD program, and we use it here at Moderna extensively. So going through now the examples, now let's jump into the case studies. So first we will talk about MIDD for therapeutics, where I will discuss how we used it for first in human dose selection. And then we will go into MIDD for vaccines, where we will showcase how we have been using modeling and simulation for our vaccines, phase 3 dose selection, and then dose selection for pediatric populations. So going into the therapeutic side first, here I will walk through the example where we had a lipid nanoparticle which encoded heavy and light chain of an antibody. So the lipid nanoparticle with mRNA encoding heavy and light chain of an antibody is administered in vivo to animals, and then this mRNA expresses these functional proteins, and a functional antibody is secreted out of the cell by using mRNA technology. So at our end, when we were developing this model, when we only had non-clinical data, the objective was to understand rat to human translation of PK and PD responses, and then to predict what the human response would be based on the translational understanding that we gained while modeling those outcomes. And these are some of the data that we had. So we had data across various dose levels in RAC and NHP after IV administration, and we had PK and PD readouts measured over time. So what we know from small molecules and antibodies is uh, that as we go in higher species, the different rates of metabolism, of absorption, elimination, they slow down. Why? Because if you look at heart rate in rats, for example, it's much faster than in humans. Blood flow rates are much faster than in humans. So overall, small animals are the systems are much faster than what we have in humans, and we see that resulting concentration time profiles that show that the elimination profiles are slower as we go up in humans. So this is something called principle of allometric scaling, that as we go up in species, the time course of response lasts longer due to that slowed metabolism and overall system. This principle works very well for small molecules and antibodies. In most cases, there are exceptions, but for our case, we wanted to see if this applies to mRNA PK as well. So we embarked on the journey and used our data that were available to build a PK/PD model. So here, this is a model schematic where we model it using compartmental models. Each compartment is an ordinal differential equation, and the rates and to and from different compartments are modeled and parameterized using several understanding of physiology and some of the parameter bounds that are possible. So top portion is a PK model. Once there is drug concentration, then we link it to the PD response. So the IgG is the PD response that we had with this mRNA 1944, and that is also linked via this PK/PD modeling framework. So now let's look into the data. So here, what is shown is plasma mRNA PK profiles over time in rat and NHPs. And as you can see, the half-lives in rat and NHPs are different, where rat we have a shorter half-life, NHPs we have a longer half-life. And when we apply the principle of allometric scaling in the modeling framework, we can fit the data across both species by applying those exponents of clearance and rates. So body weight based allometric scaling described the mRNA PK well in rats and monkeys. Then we looked into PD, which for antibodies, it is well known that allometric scaling works quite well. And in this case, also it worked beautifully, where the observed data fitted quite well when this principle was applied. So once we have a translational model and we can describe some of the interspecies differences using some of the known principles that we have, we can then use that model to predict what human response would be. So we had at the time, the question was what dose should we select, what dose range should be taken in the human clinical studies, and whether that dose is going to lead to concentrations that are deemed to be effective in humans. So we used this translational approach, extrapolated to humans using the same allometric principle, and predicted what the outcomes would be in humans. So here, this is the prediction across three different dose levels, 0.1, 0.3, and 0.6. The solid line is the median prediction, and the shaded area is the prediction interval. And Based on this, and there were many more other simulations done, and these are the doses that we ended up selecting based on the model simulations. Um, and 1 microgram per ml was the threshold that we were targeting, and we wanted to see that those concentration last over a certain period of time. And we can see here that at zero 0.3 mg per kilo, they would last at least up to 4 months after a single dose. Then we actually conducted the clinical trial and we got the observed data. And now let's see how the observed data overlaid with what we predicted a priori using non-clinical results. So as you can see here, observed data overlaid very well with what we had predicted at all 3 dose levels. We were very happy to see this because this was the first time ever when a mRNA based therapy was used to uh, produce antibodies within an individual. So it is our own body producing the antibodies by administering mRNA, and we got a very nice dose dependent response at these 3 dose levels. And it also was very exciting to see that how the translational framework that we had worked so well in this case. So we are using this across many other programs, and each different modality, each different target has its own different considerations that we take into account in predicting responses for humans. So in summary, administration of mRNA 1944 resulted in dose-dependent increases in levels of antibody against ChikV24 in rats, NHPs, and humans. Body weight-based allometric scaling of PK and PD model parameters adequately describe the observed PK-PD profiles in rat and NHPs, and dose-dependent pharmacology in humans was adequately predicted from preclinical species. Now, jumping on to pharmacometrics for vaccines. So, pharmacometrics for therapeutics is very widely used in biopharma industry. Um, there are many examples of stories and success, a lot of models out there, and this is something which is now an expectation in therapeutics side of things. For vaccines, this was a brand new chapter. So right now, if you pick some of the books on pharmacometrics, you will not find a chapter on vaccines. So here at Moderna, we embarked into developing these models so that we can use modeling and simulation approaches to guide dose selection for vaccines as well. Uh, uh, and especially in clinical development, dose selection setting where we could influence those decisions. So how we embarked on the journey. So we set out to develop pharmacometric models for our vaccines. The model describes the immune response stimulated by a vaccine and the resulted immune dynamics. So we call the model immunostimulation immunodynamic model, or ISID model for short. Now let me walk you through the model development. As with all pharmacometric model, we have to first understand the underlying mechanism of the medicine, or in this case, the vaccine. With vaccines, we know that they stimulate immune responses after each vaccination, and immune responses can be measured in multiple ways. The most common and widely accepted measurement of an immune response after vaccination is measurement of the neutralizing antibodies. Here we are looking at a typical time course of neutralizing antibody response generated after vaccination. After each vaccine dose, our body generates an immune response via immune stimulation, which persists over a certain period. In developing model, we first set out to mathematically describe the underlying mechanisms of immune stimulation and dynamics of this response. So what are these mechanisms and how do we represent them mathematically? So here, this is a simplified conceptual representation of mechanisms underlying the generation of neutralizing antibody response following vaccination. Following the first vaccine dose, naive B cells are activated to produce antigen-specific antibody-secreting plasma cells. Some of those activated B cells form memory B cells, which are amenable to activation upon second vaccine dose. After the second vaccine dose, naive B cells as well as memory B cells are activated to produce antigen-specific antibodies. These are the underlying mechanisms, but how do we represent them mathematically? Well, there are a lot of mathematical equations that were needed to describe this. We started out with simple models, and then uh, saw if the model was capturing the observed data and what else was needed to be included, what are the different functional forms that are needed to describe these responses. And these are the some. And at the end, we had a model that had 10 differential equations and 17 parameters to adequately describe the time course and stimulatory dynamic effects that were said. Now, to understand all of these differential equations, I will need to give you a walkthrough of each equation, what each parameter is, but I will spare you the pain and not go into all of those details here. Um, and I just wanted to show you that what it looks behind the scenes. Uh, so here, why develop such a model and what is the use? So the key questions that were in front of us, and there are many questions that can be answered, like what is the dose, what is the regimen, what, and what are different correlated effects. But here we will focus on two main questions. So first one is what vaccine dose should be used in clinical studies, and the second, how do we select doses for different age groups? For me personally, the most important question was what vaccine doses should be given to my 6-month old son and 2-year-old daughter. So it was a very personal thing, and it is incredible that we had a chance to work on something that our own children would get. So uh, the two examples that we will go through are here. So first one, we will review the ISID and reactogenicity modeling for our CMV vaccine. Uh, and I'll walk you through that first, and then we will go into ISID modeling for our mRNA 1273 vaccine, where we used it for our pediatric dose selection. When we we began developing these models back in 2019, we had phase 1 clinical data readout from our CMV vaccine. So our model, the development of these models began before the pandemic, when COVID was not around. So we started way back then, and since now we have these models, we were very nicely and readily able to use it for our COVID vaccine as well. So what is our CMV vaccine? So our CMV vaccine includes 6 mRNAs that encode 2 antigens, 5 encode the pentamer, and 6 encode the GB antigen. And each antigen infects different cell types. And we have developed ISID models for both antigens. We began so we began developing data with our phase 1 data in hand. So here uh, we had data for neutralizing antibodies against epithelial cell at different dose levels, 30, 90, 180, 300 at different time points measured. And then we wanted to see if we can describe this using the mathematical framework we had. And this is the data for our antibody response against the GB antigen. So we had both of these data and used this for developing our ISID model as well. So we went through hundreds of iterations to find the optimal model structure, parameters, and then qualified our ISID model for neutralizing antibody titers against epithelial cell infection based on various numerical and visual diagnostics. Our final model described the observed data well. Here the dots are observed data, and solid line is fitted mean titer levels, and shaded area is the 5th to 95th percentile interval. As you can see, the model adequately captured the central tendency of the data as well as the inter-individual variability. we did a similar exercise for our GB antigen data, and were able to qualify the model using different numerical and predictive diagnostic. So once we have a qualified model, we can use it for performing clinical trial simulations and answer some of the questions that are at hand. The key question that we had in front of us was, which dose should we select for our phase 3 clinical study? And as I previously mentioned, a selection of a phase 3 dose is one of the most important decisions during development of a drug, as it could uh, lead to maximize the success tremendously if we are good at making those decisions. So here we used our model to simulate relationship between dose and neutralizing antibody titers across a wide dose range, and evaluated which dose is expected to yield neutralizing antibody titers above the benchmark of natural infection. In this plot here, dose is on x-axis and neutralizing antibodies at 1 month post third dose are on the y-axis. Solid blue line is the geometric mean titer, and shaded area is 5th to 95th percentile prediction interval. We we saw that a 50 microgram dose was enough to achieve GMT above the GMT benchmark of natural infection for both epithelial and fibroblast cell infection. We could possibly get a greater response if we went to 250 microgram, where the titer exceed the benchmark in majority of population for the neutralizing antibody against fibroblast cell infection. But dose selection is not just about efficacy. We also take into consideration safety. So how about adverse reaction at those higher doses? So in order to model the relationship between dose and adverse reaction, we used a typical logistic regression model. Here on the graph, we have at a given dose, an individual may either have no adverse events or they may. And we do this, we collect data across a variety of different adverse events that are there. And once that data is available, we can use it to derive a probability of such events given a certain dose. And once we have that kind of probabilistic analysis done, we can derive something called a composite risk score. Composite risk score is a combined probability of having any adverse reaction. On the slide, you can see the composite risk score on the y-axis and dose on the x-axis for each vaccine dose. Uh, Composite risk score was modeled using data from our phase 1 clinical study. Probabilistic modeling helps to produce a continuous relationship between dose and risk of adverse events. So even at doses that are not evaluated in the clinical study, you can have those continuous relationship build, and you can visualize that where are the curves bending in a way that we do not want them to bend, and then we can base our decisions where the those risks are minimal. So now if you look at our 250 microgram dose, which gave us really high immunogenic titers, we can see that the risks are slightly higher. They are not way high, but the slightly higher risks of grade 3 reactions at 250. If we dial down the dose at 100, then the risk of those grade 3 events, which and grade 2, grade 1 also, is low. So it appeared that 100 microgram would be a favorable dose from a safety standpoint. Now, if we go back to our dose response relationship from the efficacy side of things, where there is where we see immunogenicity, we can see that 100 microgram dose had a lower had antibody titers that were above the benchmark of natural infection in majority of subjects. And uh, the basis of dose selection is to maximize immunogenicity while retaining minimal risk of adverse reactions. So based on both safety modeling and efficacy modeling, uh, we selected a phase 3 dose of 100 micrograms for a CMV program. This dose is now an approved dose for our phase 3 trial, and our phase 3 trial is successfully enrolling patients in this study at this dose. So we did all of this modeling and then submitted all of this work at different regulatory agencies globally, including US FDA, EMA, TGA, and many other countries across the world using the PUMA software. Now we are switching gears to ISID modeling for our COVID-19 vaccine. Here we will see how we successfully use this modeling approach for our pediatric dose selection. For our COVID vaccine, at this time we had a lot of data. We had data available from 2567 subjects from our phase 2 clinical studies in adults, adolescents, and older children, which were greater than 6 years of age, and from our phase 3 study in adults. The modeling approach allows for pooling of data across different studies and helps to derive inferences from totality of clinical data. Versus if we just look at observed data and try to make our decisions, then you're looking at one set of data at a time. Using a model, you can integrate all different studies and get a holistic understanding of our responses in different age groups. And then we applied some of the scaling mechanisms that is there to predict what doses would be in our pediatric trial. So how this was done, we adapted our ISID modeling framework to we developed for CMV vaccine to COVID, and we optimized some of the parameters that were specific to COVID-19. We assessed dose and age as covariates on antibody titer response, and then simulated antibody titers at various doses across different age groups. So what was our goal? Our goal was to predict which dose level in young children and infants would yield neutralizing antibody titers that are similar to young adults. On this graph, the reference immunogenicity data is from our phase 3 COVE study in young adults. And then we used our ISID model to simulate distribution of antibody titers at different doses. And then we use it to evaluate. We did this for a lot of different dose levels, and this was before we did the actual pediatric study, the large trial. And the real question was what kind of doses will be effective. If we have a 100 microgram dose in adults, what dose is going to yield similar antibody response in young population? And for vaccines, this kind of modeling is very new and done for the first time. So once we have simulated this, we compute a metric called GMR, which is geometric mean ratio, and then there are some set criteria which are accepted by the regulators that meet the statistical criteria to either pass or fail based on the results that are obtained. So using simulations, these were the results of our simulation back then. This was done in fall of last year, where we simulated at different doses, 10, 25, 50, and 100. And then based on model simulations, we predicted that a primary series of 25 microgram was predicted to meet the non-inferiority criteria in young children and infants. As I said, it was back in August last year when observed data in these age groups were not available. The model predictions were useful in selecting doses to evaluate in the clinical study. Now we have actual data here that we got from our clinical studies. We actually conducted those trials and got our data. And I'm extremely happy to share that what we predicted back then in fall lined up with what the observed data showed when we received those data. And as you can see, the observed data closely correlates with model predictions, validating our modeling predictions and the modeling approach, and shows that how integrating the modeling and simulation workflows during the clinical development pipeline can help in sound decision making for our dose selections and can lead to maximize the rate of success. So, in summary, modeling and simulation helps drive data-driven decision-making for clinical dose selection. Traditional PKPD models are widely used for therapeutics, and we have adapted those traditional PKPD models for to vaccines. ISID models can be used to successfully predict neutralizing antibody responses across various age groups, and our ISID models can predict a priori immunogenic responses in various age groups. And we have demonstrated utility of these models for phase 3 dose selection for a CMV vaccine in this case, and used this successfully for a pediatric dose selection for a COVID-19 vaccine. And thank you everyone for your attention and listening to my talk. At Moderna, our pharmacometrics team is expanding. We are hiring. We have several leadership roles in different therapeutic areas. This is just the beginning for mRNA medicines and mRNA science. There's a lot more to be learned, done, and a lot more people to be helped suffering from different variety of conditions and diseases. So we have different, apart from vaccines, we have autoimmune therapeutic area. There is oncology. There are a number of programs there, and there are rare diseases. And we are also building a QSP modeling function within our pharmacometrics group. So if you or anyone you know who has the skills, please go on our website and apply for these positions. Yeah, and that's it. And many thanks to our a lot of work has been done in collaboration with our Pumas.ai team there. In particular, Vijay has been one of the key individual who we have collaborated with over several years in testing, validating, deploying the Pumas, and also consulting for clinical pharmacology and pharmacometric, leading to some of the regulatory submissions. And yeah, so many thanks to them, and yeah, that's it.
Thank you, Hussein. There are some questions. One of them is, what are the biggest challenges you're facing with software tools when you do these kinds of analyses?
Yeah, so one is the integration of different workflows, right? So in when we think about therapeutics, one minute, let me just move this here. Yeah, so different software, so for different types of analysis, we have different software tools where we go into those softwares, do the analysis, then results from those analyses are then imported into other software tools that then do those analysis. And so we have to like keep jumping between different tools. That is one. It is not a challenge, but a kind of a hassle. People, but if something can do within a single software, then we would prefer that. Uh, then other challenges, like these are software tools that are there since quite long time, and there has been some progress, but not a lot of progress. So. Like some of the time efficiencies and things like that, uh, if you see a few seconds of improvement in time on a small model, think about if you have a large model, and that saves you maybe 1 hour, 2 hours, and if you have to run those models hundreds of times to validate test, uh, so that is a challenge. And if we have something that is faster, then we can actually use that model to drive a decision, because decisions are timely. If we do not get our data models predictions in time, uh, then we are not able to help influence that decision, because decisions are to be made when the time is in constraint. So yeah, so that is the big one.
Thank you. There was one question. Do you have any specific experiences within the teams using Julia before they came convinced it was a good tool that made people go, okay, this thing is cool, we should use it?
So I was introduced to Julia via Pumas. So when Pumas came along, and me personally, I was intrigued by how everything else can be integrated within a single workflow, especially the simulation workflows. Some of the tools that we have, the simulation workflows are very time consuming, and here in Julia, it is once you have a model, it is very easy to get into those kind of things. So that is where got me intrigued. And then it was a journey to test and validate over time, and we did that in record time here. Yeah.
Okay. Moderna has been very successful in applying Julia-based software to PK/PD modeling. Which other areas of drug discovery do you think could benefit from Julia being used more widely?
Um, uh, so there could be applications across all sorts of um, modeling, right? So this is ordinal these ordinal differential equation models are used in even uh, manufacturing, like so some of the reaction systems that are there, uh, there it can be applied. But again, some of the uh, benefits and things like that will need to be weighed there, where how practical is it to jump from the current tool to a Julia tool.
Yeah.
Yeah, if because those models are not that complex, and the gain in efficiency, how big is it? So but I can certainly see that it can be used there. Then there are computational side. I think there are other departments already using it at Moderna. uh, yeah.
And maybe as the last question, you showed models that worked well. How often does it happen that a predictive model turns out to not be working once you acquire it and then verify the data afterwards?
So it is a continuous learn, confirm, predict cycles. So uh, it is not that one we create one model and that's it, model is set. Then at the end there is a because if we go from a very uh, old or model which is informed by very little data and compare that with the final, it may not correlate. So the journey is to guide at every stage. So each stage there are different questions. So for to answer a question, this is the model, this is, and we are able to at that micro stage, we are able to do quite well in guiding that. Then once we get more data, we keep on updating. So for example, our COVID model, uh, where we had that 2000 subject data, that was a lot of data that went into that model. So with that kind of data, then in likely cases we are able to successful, as long as the model is good enough, tested, validated in a way that should be. Yeah. The cases where it may fail is, let's say, there is a preclinical model uh, which you base certain assumptions on, and you go into humans with certain unknowns, that how much is the receptor density, how is the um, expression of certain targets within the body that clear those moieties. And if those are off by huge amounts, then your predictions will look not very much aligned. Uh, so that is where we do all kinds of sensitivity analysis to see that, hey, what kind of things, which parameters are important, and if they vary by a certain extent, then what will happen here.
Thank you. Thank you for the insightful talk, and I look forward what Moderna does next with Julia.
Thank you.
Next, let me welcome Martin Pravenberg. He is the Vice President of Engineering at Relational AI, and he's here to give the sponsor talk of Relational AI. Welcome, Martin.
All right, thank you, Jonathan. All right, welcome everybody. I hope everybody is having a fantastic conference. I'm certainly enjoying the breadth of material that's being presented here. It's all super interesting. So in the next 15 minutes, I'm going to briefly highlight what we do so that you have some background on what we're building as a product. And then I'll dive into how we're using Julia and what we're contributing to Julia in our product. Yeah. All right. So first, so what Relational AI is building the next generation database system for intelligent data apps based on relational knowledge graphs. It's kind of a mouthful, so I will explain a little bit with examples what that means exactly. But it's important to remember that at the core, we're a database system, and we want to develop intelligent data apps, and it is relational. Yeah. So I listed a few of our target workloads what we aim to support, so that you kind of have an idea of what we want to do. So that is reasoning. I'll show some examples. Graph analytics, JSON, semi-structured data analytics, mathematical optimization, and relational machine learning. Okay, and this is at the core built with Julia, and I will highlight exactly later which parts are in Julia and how that is working for us. Okay. All right. So to give you a quick impression of what kind of things we envision to build is let's imagine that we are going to build an intelligent data app for flight data. So you all have used airplanes, of course. You know there's flights, they can get delayed, and there's historical information. There are busy airports, and so on. So imagine that you want to do all kinds of analytics over that, where let's say you want to know which carriers have the biggest delays, or is there maybe in winter are the delays longer, or at the end of the day are the delays longer. You may want to do some planning and optimization and so on. Yeah. So how would you do that? Now, the FAA actually publishes data on flight delays, and this is an example of that data inside a BigQuery. And while this is great that we have this data available, it is really hard to work with if you don't actually, if you're not human, and if you don't know the schema. Like I pointed out some problems with this data set is that, for example, like here there's a call as flight time, and there's a number there, but yeah, what does the number mean? Is it minutes? Is it hours? Is it seconds? Is it something else? There is some peculiar things, like, for example, if the flight is canceled, then the flight time is 0. So now imagine that you're going to compute an aggregate over this data set, and you forgot to exclude the canceled flight. Then you have some really quick flights in there that are messing up your aggregates. Yeah. So generally, the quality of models is really problematic. And this makes it hard to work with and write correct business logic. So what we do is that we allow you to define better models. So, for example, you can very easily define that, let's say, an heliport is a subset of airports with certain properties. You can define that very clearly that when a flight is cancelled, you're not working with strings, let's say a string y, and you have to guess what that means. You can very clearly define a relation of all the flights that are cancelled, and then you can very clearly use those in your queries and your business logic that you write over it. You can turn data into data that is units of metrics. Like, for example, an arrival delay is the maximum of the 0 and the delta that we saw earlier. Yeah, and we're going to say that is minutes. So now in the model, we have very precise information that this is actually a minute. Yeah, and you can do stuff like, let's say, where you can work with coordinates of airports, where you can very precisely use the units of distance that you're working with, whether that is feet, meters, or kilometers. And you've all heard the horror stories of things going wrong when you're dealing with the wrong units. Yeah. So the language that you see here is REL. So REL is a declarative query language that is used by our system, and that is implemented in Julia. So to show you some examples that go beyond modeling, is you can add reasoning in the system as well. So, for example, if X is located in T and T is located in Y, then you can derive a new fact that X is also located in Y, so that you can compute transitivity. You can compute the distance between airports by using the coordinate and a distance abstraction that computes from the positions on Earth where what exactly, given the Earth radius and all the units of measurements, what the distance with those airports is. That is added to your model. Like, imagine that it shows up in your database, let's say, as a normal relation that you can query, and you can use that directly in your business logic. Yeah. We also really care about data integrity. So you can, in the same language, you can define integrity constraints that protect your data from getting in a bad shape. So you can, for example, say is that if you have an origin relation, that it has to be a relationship between flights and airports. You can also say that a flight has to have an origin. You can't leave from nowhere. You can say that a flight only has one origin. And for example, you can say that a cancelled flight cannot have a flight duration, and that a flight has to be either cancelled, diverted, or arrived, and not any kind of other combination of that. Okay? All right, so this is just to give you a very quick taste. I didn't explain this very well, but it's just so that you have a quick idea of what we do. Okay? Now, so this is the overall architecture of our system. Our system is available as a service. It is deployed in the cloud. Our databases are stored in durable object storage, like imagine S3, let's say. And then we are running all the business logic and the queries and all the data loading and all that in transient engines that we provision that use the scalable durable object storage. Yeah. Now, in these engines, there is a database server process, and that database server process is implemented with Julia. Okay. Now, so on the client side, we also have SDKs, like just how you have, let's say, you have SDKs for Amazon Web Services or for database systems and all that. And one of those SDKs that we have is also for Julia, and Julia to us is a tier 1 language where we have SDK support for. Okay. All right. So I wanted to briefly highlight like how we contribute to the Julia community. So we have quite a history with the Julia community. We've been at many JuliaCons, like we were there in 2018. It may have been the first. I'm not entirely sure that this was the first day we were at. And there's many different packages that we contribute to now. So of course we have our own Julia SDK. It's already great that we have that. But we have also open sourced new packages that we found key in the development of our product. So there's a package called Salsa that we use for incremental computation that was presented at JuliaCon 2020. We have a package called Blobs that we use for the manual layout of our data structures, our B trees in the database system. That was presented at JuliaCon 2018. We have contributed to the performance of fixed point decimals. We use those directly in our database, like imagine a decimal data type in SQL. That is basically what this package is, what we use for our implementation of decimals. Recently, we started sponsoring the DuckDB project. And DuckDB now has a library for Julia. And DuckDB is an amazingly flexible, awesome SQL system. And so thanks to our contributions there, Julia now has an official package that is sponsored by that's developed by the DuckDB organization that you can use. And you can use that in data frames that is independent of our product. Yeah. Now we've been hiring over the last year a variety of people that are core to the Julia engineering. So some people that contribute to Julia, the language and the system itself, and some in the packaging ecosystem. So really one that many of you probably know, Jacob Quinn, he now works for us, and he is full-time working on things like improving HTTP libraries, JSON libraries, CSV libraries, error libraries, and so on. There's also a package under development for protocol buffers. There is already a protocol buffer package, but it is dynamic and not highly performant. We're developing a version that is optimized for performance that we'll hope to announce that soon. And we are about to embark on a gRPC implementation. If you're interested in gRPC, please reach out and maybe we can collaborate on that. Now, because we use Julia in production with a database system, which is maybe a slightly different use case than many of you are currently doing, we have all kinds of needs on monitoring and production users that are kind of unique to us. And so we've also, for example, developed a package called Servermetrics that allows you to instrument code bases to collect metrics very conveniently. And those metrics are then submitted to Datadog or Prometheus. That package is open source, and it was developed by one of our colleagues, Dana Wilson. This year, we have contributed a memory allocation profiler. Nathan and Pete presented that earlier this week. I'll have it on the next slide. I'll highlight it. I will go check out that talk. This is one of the tools that we needed to better analyze the performance of our system. And we decided to help make sure that the Julia community can do this effectively. In Julia 1.9, there is an interactive thread pool feature upcoming that was developed by Kiran Palnani and various other people. What that allows you to do is to schedule tasks that you really do not want to be compromised by long-running computations. Like what the problem that we had, for example, is that in our production environment, there need to be events submitted, that the process is healthy, and metrics need to be submitted into the system and all that. And those tasks were not kind of scheduled appropriately. And so with the interactive thread pool, you can make sure that these are really, really happening. Yeah. And we are also embarking on helping out with garbage collection performance and potentially integration of MMTK. There were various talks about that this JuliaCon, and we are sponsoring the MMTK project. All right, so there are more things that we do, but these are probably the highlights. Yeah, so go check out the memory allocator profiler talk if you haven't seen that yet. It's really cool. So what it can do now is that you can profile which types are being allocated, what the call stacks are. You can visualize them with pprof. It's available by default in Julia 1.8. And thanks also to Valentin for helping a lot with this, and Pete and Nathan from our side helped with that. Okay. All right, I want to show you a little bit about the company to show you like what is behind it. So we are a 170 people company now. There are quite a lot of people in there from various backgrounds that are very interesting. 120 of those are computer and data scientists, and 50 of those are primarily writing Julia full-time, basically. That's their primary job. So we have 50 people writing Julia on a daily basis. We now have a 5-person full-time Julia engineering team. So those people are developing packages for Julia and contributing to the Julia system overall. Our code base is 150,000 lines for the core product, which is fairly concise for a database management system. So we're happy with that. And then there is about 80K floating around of other reusable libraries that you could potentially open source, but that we're not ready for yet in some cases. We have 100,000 lines of Julia test suite code. And then in our own language, we have 32,000 lines of code. So our system is in production. We have an automated CI/CD pipeline that compiles our Julia code into binaries and deploys that into our system. Every commit triggers 27 hours of test cases. And in total, we're running 1,000 hours of builds per day, of course, over multiple machines. Otherwise, that wouldn't work. And in a production deployment, currently, we're executing 2,500 transactions per hour. We expect this to grow very quickly because our product is only like deployed with first customers right now, and we expect this to tremendously grow over the next year. But it's already interesting to see that there is a live Julia system that is processing about 1 transaction per second in a production environment. The customers, so like I said, the product is in production. We have paying enterprise customers. I can't list them. But they're large and they have complex business logic problems typically. And we're also well funded. We have raised in total 122 million. This year we had a Series B of 75 million involving Tiger Global and others. All right, I want to briefly comment on what we see next. So like we think it's really important to have foundational packages available for systems, like around, let's say, protobuf support, gRPC support, Parquet, Arrow, Iceberg, and so on. That stuff has to work really well and be very efficient. There's already a lot of work done in there, but it can still be improved. It would be great if there's more and more high-quality SDKs available for cloud providers that we would use. And of course, we will continue to invest in anything that is needed for production usage of Julia. We're also interested in performance a lot, in particular in scale-up performance. So scale-up means that you use bigger machines with more cores and large amounts of memory. So we've observed that Julia scales very well in tight inner loops. But if your application does occasionally allocate, then the scale-up performance could be improved. And we are engaged in trying to make sure that that gets better. We're also really interested in static analysis. Like, for example, what we regularly observe is that, let's say, if you have a code path that does error handling, if there's a bug in that code path itself, then you will not see your error handling. And that's a big problem. And so we're really, really glad to see it yet now in 1.8. And we're planning to expand in that and maybe start contributing to it. And then we're really interested in improving Julia interoperability. Like in principle, we're a service, and it doesn't necessarily matter what the service is implemented in, which happens to be Julia. But it would be really great to have also extensibility to Julia within the system. And so we're looking into like how can we extend the system in some way. And currently, this is often done with WASM and JavaScript and all that, which is due to the sandboxing capabilities that are there. All right, that was it. There's a few much more elaborate talks available online that came out in the last year. If you're really interested in the technical details, I would watch the CMU talk, CMU Relation AI, that dives much more into what we do. And then there's some other talks available to give you more background on applications and sort of the area where we operate in. Thank you very much.
Thank you, Martin. Maybe time for one quick question. What is the thought behind having your own in-house language?
Yeah, that's interesting. It's hard to answer. Maybe join for the panel as well that we have later. Like we need to write very expressive business logic. It's often highly recursive. So SQL is not adequate for that because of the recursive needs that you have. And also like it's often like we have thousands and thousands of different relations and definitions involved. So SQL is not designed for that kind of skill. And we need a declarative language, so not necessarily Julia, because we want to automatically parallelize and distribute and optimize that code. And like, while Julia is fantastic, it's not necessarily great for that. So that's sort of the short answer.
Thank you so much. It's now my pleasure to invite Jeff Besançon. Jeff is a co-founder of the Julia language. He's now at Julia Computing, and he is going to give the State of the Julia 2022 talk.
Thank you, Valentin. Can you hear me okay?
Yes, we can.
Great. All right. Well, it's great to be here talking to everyone. And actually, that's thanks to Martin, because that his talk there is a pretty good segue into this, because he's also thinking about where Julia needs to go next and where we are now. So this is a time we like to kind of take stock of the previous year and look at how the language and ecosystem are doing overall, and maybe highlight some things that are going on that people might not otherwise be aware of. So several Julia contributors also contributed to this talk. But I'm giving it, so it's going to be a little compiler heavy, hopefully unsurprisingly. So the last year was actually a really big year for features. We've been doing 1.x releases for a couple of years. We have quite a few of them. You'd think we've kind of gotten through all the obvious features, but we actually hadn't. And just this year, a lot of kind of big ticket, long-standing, or you could say obvious kinds of features that we never had actually got done. So for example, you can declare a field of a struct const, and then you can't modify it. And that's good for enforcing invariance, and we can use it to optimize. So that's a nice feature. And similarly, you can also declare fields at atomic. And you can also annotate operations like increments and the typical set of those kinds of operations as atomic for multi-threaded programming. And that might be sounds a little bit like a low-level detail, but it's actually very important because we like to ask ourselves, are there any reasons that you couldn't write some code in Julia? Is there any reason you'd ever have to use C, for example? And this was actually one of those. To do certain kinds of threaded programming, you need these operations. And C exposes them, and Julia didn't. So we had to fix that, and now you have that in Julia. So you can do all kinds of things like, say, writing a scheduler for tasks in Julia itself. So that extends the range of the language. It's nice. Type declarations on global variables. People have wanted it a long time. We have that now. ND array and concatenation syntax as well. And the news from the left-hand side of the equals, as it were, is we now have property destructuring in addition to the usual positional iteration-based destructuring. So you can destructure by name, and we also have slurping in any position. So you can put the ... anywhere in the argument list and collect, say, the first and the middle and the last elements. And there's also this nice try catch else, where you can have a block that's executed if there were no errors. So really a bunch of nice features just in the last year. All right, and there are a bunch of compiler internals, interesting things going on as well. So I've got a list here to give a quick overview, and then I'm going to drill down and give some more details on some of these. So we added the ability to separate the LVM dependency and native code compiler from the runtime so that they become optional. We also added the ability to strip debug info, metadata, and even the Julia IR out of a built system image. So this is something people want for shipping or deploying applications. They don't want their doc strings and things like that in something that they ship to someone. So now there's an option to remove that. There's this very interesting project, static-compiler.jl, going on. There are improvements to pre-compiling to address latency problems. And we have a couple interesting new capabilities in the compiler around effect analysis and escape analysis I'm going to talk a bit about. And we also added some early finalizer insertion. So if you have an object that has a finalizer and the compiler can prove that it reaches the end of its lifetime at a particular place, the compiler can now insert an eager finalization call to free up resources a lot faster. So that's really cool. And our Lvm Pass Pipeline has been improved a lot. And we, in particular, we've now enabled inductive range check elimination, so we can automatically eliminate a lot more bounds checks than we used to. Still not all of them. We'd like to be able to automatically remove all the bounds checks, but that's very hard. We don't have all of them yet, but at least there's more. We can do more, and that's just an ongoing process. All right, so just some more detail to get a picture of some of this. So if you look at the Lib Julia 1.7 runtime, it's about 3 megabytes, but it links to LibLVM, which is over 60 megabytes. That's why I've got it going off the slide there, because it's if you do it to scale, it doesn't fit on the slide. And so it links to that. So it's a pretty heavy dependency to carry around. It's one of the reasons why if you try to deploy, say, a Julia system image to run somewhere, it takes up so much space. That's one of the reasons. So what we did now in 1.8 is there's a separate library, Lib Julia CodeGen, that links to LVM, and Lib Julia only optionally links to the CodeGen library. So Lib Julia is now a little less than 3 megabytes, but if you want to, you can drop the LVM and the CodeGen part, and you can do that actually by just deleting them. And we will see on startup that they're not there, and we'll just we won't use the compiler. So now that goes from, almost 70 megabytes or so to have a Julia runtime. Now you only strictly need 3 megabytes. But of course, you have to give up the JIT in order to do that, but that's possible in some cases. So staticCompiler.jl is kind of another very different kind of approach to the produce deployable or small executables sort of problem. And speaking of which, I really liked Jeremy Howard's keynote, and it just so happens that we've been working on things leading towards basically his big ask, which is make it easy to build executables that you can hand to someone. And so it's we happen to be working on that, so that's good news for him, hopefully. So this project, it's a different approach where basically you can give it a function and a type signature to compile it for, and it will attempt to emit a small object file with just that code. So like in this case, you get a .o file that's 992 bytes to do fib. So this is this is a kind of a hack. It's pretty cool. It's actually built on top of the same infrastructure that the GPU compiler uses. It's essentially like instead of using the same kind of rules and restrictions that things have to be statically resolvable that you need on the GPU, but just targeting the CPU instead. And so as such, it does not support the whole language. So there are lots and lots of things you can't do in this. But I think over time it will be able to support more of the language. So we're kind of tackling this problem from both ends. So in static compiler, hopefully the coverage of what you can do in the language will gradually increase. And then from the other end, starting with the full current runtime in language, we will gradually find ways to make it smaller. And hopefully we'll meet somewhere in the middle and we'll just have the best of both of those worlds. So we'll follow along with that. Pre-compilation. So Tim Holy did a bunch of work on this this year. So a problem we had in the past with caching pre-compiled packages is that for a given package, this green package here, we could only cache specializations that it did of its own methods. So if it called something in a different package, in package B, we would find out about that method, that specialization being needed, but we wouldn't be able to save it with the code for package A. So that limited the number of things that we could save, in the hopes of reusing them when we reload. And so that has been fixed. So that method now turns green, and so we can save that. And this is the result. This is from Tim's PR. So basically, it shows that the file sizes are a little bit bigger, and the package load times are a bit longer sometimes because we're saving and loading more stuff. But the latency is smaller. So this is the TTFT is the time to first task, and so that is with the orange and green bars that we can do now. Those are lower. So this is good progress. It's the direction things need to move in. Of course, we don't have the ability to cache native code yet, but that's the obvious next step. And the good news is that if we can do that, that's really going to be a much bigger impact, because generating the native code is the slowest step, and it's the one we're not caching yet. So there's still a lot of gains available there if we can do that. And hopefully, maybe in the next year, that will happen. So inside the compiler, there's some nice new toys. So we have this thing called effect analysis, where we can basically deduce what kinds of things a function does. So if we can ask for infer effects of, say, plus of 2 ints. So that's just plus of ints is basically just a totally pure function. All it does is return that value, and nothing else observable happens in any way. So that's why these things are all green. So no funny business happening in plus of 2 ints. But if we ask about sign, it's also mostly green, but there's this one red N. So the N actually stands for no throw. So it's a kind of a weird double negative happening here, where it's not no throw, which means it might throw an exception, because sign of an infinite value throws an exception. So that's something we need to know about. So for instance, if a call might throw an exception, that limits where the optimizer can move it around, because we have to make sure we don't, remove an exception that's supposed to happen in a program. Or then if you ask about something that mutates, like a set property, we see then that also has this E thing, which is basically means like a mutation effect that someone else can observe, because someone else might have a reference to this ref cell. So it might do something that's observable outside. Or then you have something like print, which is just, print prints. So that's the classic example of a side effect. So that is just, that's just deep red. So this is really neat, very accurate information that our compiler has that gives it a lot of freedom to optimize more things. So for example, if we just did a simple 2.0 to the integer 4 power, which is implemented in Julia, of course, like basically all of our math functions, they're written in Julia itself. So in 1.8, if you did that, you'd see the code we generate still has a call to the power function there. Even though all the arguments are constant, we weren't able to prove that it's safe to evaluate it at compile time and preserve the behavior of the program. But in 1.9, we can in fact do that. So on master, and in that version, when it's released, we'll be able to remove that call and just replace it with the constant result. Because we can do that by just walking through all of the code for power and confirming that there aren't any side effects. And so it's safe to just reduce all of that to a constant. Another kind of less intuitive effect of this kind of accurate information is it actually lets us compile faster in some cases. So this is kind of a pathological case, but this is an example where we're generating code that basically calls sign on 1,000 different random numbers. So it's not typical kind of code pattern, but this kind of thing actually does come up in cases like modeling toolkit, for instance, where it's generating code and you might have a big model that has lots of constants throughout it. So that it can come up in generated code. And so what happened in 1.8, when you compile this, we see that it takes actually 13 seconds to run inference and the optimizer on it, because for every one of those constant values, we're basically trying to propagate that constant through the sign function and sort of figure out what happens and see if we can optimize it, which we can optimize it, but it's a very laborious process of going through the sign function every time and basically tracing through all the execution to understand what happens for that constant value. But now we know we can just prove that the sign function doesn't have any effects. and for these arguments. And so we know that it's safe to just call it at compile time. So instead of painstakingly tracing through the code, we know it's safe to just call at compile time. And so we can just get those constant values very quickly. And now this is, I think, about a 200x speed up for this, admittedly kind of corner case, but it's very cool anyway. There are also some improvements to inlining. You can now put @inline on a call site. We can inline abstract call sites. We can handle some combinations of some union cases and constants a little bit better. So just a couple nice improvements there. And there's still a lot to come. So we're still working on automatic differentiation with the new diffractor.jl. That's our latest attempt at that. That work is still ongoing. Actually, it just sort of picked up again just very recently. And we decided to kind of focus on that first. And based on what that needs, maybe design a more thorough general compiler plugin system based on that. But it was kind of too much to wrap our heads around to figure out what the right plugin system is first. So we're going to do AD first. And also, parallel LVM compilation is also getting pretty close. A lot of work has been done on that this year. So it's just on the cusp of maybe happening, which will accelerate our native code gen a lot, which would be that's it's a big part of our latencies. So that would be really helpful. These are better static compilation items, like I was talking about. I mentioned caching native code, and still at the back of my mind is a kind of separate compilation model for the language, which would let us do things, behave a little bit more like a C or C++ kind of language. I don't have time to go into a lot of details, but just to if you're interested in that, it continues to be at the back of my mind, but we haven't really done anything about it yet. All right, so let's check in on threading. So this is a copy of the slide from last year, where we've got things we want to do on the threading system, and we've got some some in the green state, some in the yellow state. And so let's just check in, and if you can watch the check mark switch. Okay, so some things turn green. I added an item. Some things turned yellow. So there's some progress here. It's maybe not quite as much as I would like. It's a little frustrating. We still haven't done some of these things, but we did do a really good handful of things. And in particular, I had to add an item here, this foreign thread support. It's under the performance column, but I just didn't have any space in the other column. It should be in the other column. So that's a cool new feature. And this is what it looks like. So we had this problem where if you embed Julia in a C or C++ or Java program, and you that program creates a thread and then tries to call Julia, it just crashes. Because we expect to have certain thread local state set up on every thread. So if we're running on a thread started by someone else, the state's not there and it just crashes. So that's really bad. But fortunately, starting in 1.9, this will be fixed. And we'll actually, if you call into the Julia runtime from some other thread, we can detect that situation. We see that the thread state is not set up, and we set it up, and we add the thread to the system, and actually the number of threads available grows, and we just basically add that to our pool as long as it's executing inside the Julia runtime. And so now that just works. So you can have a multi-threaded native application calling multi-threaded Julia and get scalability, and it works. So this is really cool. This is another thing. Some people, people who use Julia in an embedded kind of way, have asked for this for a long time as well. So this is really, really nice to finally have. And another issue that people hit with threads, and this was alluded to in the previous talk from Relational AI, is this issue of latency sensitive tasks. So we can, Julia is currently mostly optimized for throughput. So if you have enough compute to saturate all your cores, we're happy and we'll just do that. But if you have something that needs to respond to an IO event, it's just going to get stuck at the back of the line. So now we have the ability to start a dedicated interactive thread that will only run things that are marked as being interactive. So that sort of solves that problem for now. I think it's possible that we will extend this model in the future to basically just letting people start their own threads for interactive items. So we may switch to doing it that way, but at least for now, there is a solution in place. There's also been a lot of work on GC this year. I think if you look at the JuliaCon schedule, I think there were 3 talks about GC at least, which I think is a record, but it's very nice to see. And indeed, there's been a lot happening. So here's one example of some really good performance tuning we've done. So there's one of several GC performance issues, 40644. This was a case where if you run something repeatedly, every time GC uses 60, 70% of execution time, which is really, really unacceptable. So it's behaving a lot better now. And now we reach a steady state where it spends very little time doing GC. So that's nice. We added a heap size hint. So if you feel like your Julia process is using too much memory, we will take a hint in the GC. So it's not a hard promise. We can't, if you allocate more than this, we're going to have to allocate it. It won't, give an error or anything. But you can at least hint to the GC that, hey, please try to stay under this size. And we'll at least try to do that. And parallel marking, so we can get better scalability of the GC in multi-threaded applications is really, really close. So Diogo has gotten that there's a pull request up. It basically works. Yeah, it's really, really close. So I think that's going to be merged very soon. And we'll have a nice parallel speed up in the GC and also parallel sweeping, which Christine Flood is working on. That's also, I think, going to happen pretty soon. And then that'll address some of the multi-thread scaling problems we see in the GC. And you can also see Eduardo's talk about MMTK, which is really interesting and really amazing that he's managed to hook up a totally different garbage collector to Julia. So this is the interesting kind of experimental thing that this could work out, and we could end up with the option to use a entirely different hopefully much better garbage collector. So really huge amount of stuff happening in this area right now, which is great because GC is something we didn't pay that much attention to for a couple of years, but it's happening now. A lot of good GPU support happening. This year there was a lot of work on one API, adding support for that, and metal.jl is also coming along. So all these new backends falling into place to use with the very nice GPU support that we've got. And there was also a lot of work on profiling this year. In fact, this Martin discussed this as well. Pete and Nathan put in this allocation profiler, and Sebastian is amazing. Anytime someone does any new kind of tooling thing, it's in VS Code right away. It's really, really cool. And there's thread and task aware CPU profiling, again, also in VS Code. And this neat feature where you can profile already running code. So sometimes you run something, but you forgot to put @profile in front of it. So you can just hit a key, and it'll get a signal and tell us to collect a bit of a profile. So that's really neat. If you want to just answer, hey, what's taking so long? What's it doing in there? Neat feature. And we have package load timing. So you can do time imports and see, if your packages are taking too long to load. We can break that down and see what's taking up all the load time. More package stuff. So we got a couple nice package system features. So when you do package status, it now shows which ones can be upgraded. So what's which ones might have new versions out there. And there's better support for working with custom system images. And also, oh man, yes, this is one of these big ticket features. I've seen many times, especially people new to Julia would try to load a package and they just get an error that it's not found, and then you have to tell them, oh, you have to add it first. And I don't know how many times I told this to someone and they just said, well, why doesn't it just do that automatically for me? And why not indeed? So this is really a common request that now, thank goodness, it's finally landed. It will now prompt you to install a package if it's available and you don't have it. So you can just hit enter and it'll just go through. So that's really nice. And this was, you might wonder why this took so long. There isn't a really good reason, but it was actually a little bit tricky to figure out exactly how this should work. You don't want to put too many hooks into, the language, to make like an interactive prompt happen when you're loading a package, so it's a little tricky to work it out. It's implemented entirely inside the REPL, and it was just a little bit fiddly to figure out, exactly what it should be based on, especially because the language supports metaprogramming and that kind of thing. So, how do you know what qualifies as a using statement? So it's a little bit tricky. So, but we picked something that we think works well. But so it's finally done. And the number of registered packages, I think, is pretty cool. We seem to have had 2 doublings in the past 4 years. So I think this is really exciting. I think this is pretty good growth. From 2000 and 2018, 2020, 4,000, and now another 2 years later, 8,000. We just crossed 8,000, I think, earlier this week, I believe. So this is really cool to see. So in terms of Julia releases, Ian Butterworth put together this interesting graph of how long is it taking us between releases. So we had originally intended to put out a minor release about every 3 or 4 months. And so we sort of did that initially and noticed that, the releases since 1.0, they are coming out more quickly than they did before that time. But we can see that it's creeping up. So gradually, each release has taken generally a little bit longer to come out. And now we're creeping into the 5-6 month kind of territory, which is not so great. It is taking longer than expected to stabilize releases. I guess the good part of that is we really do take our time to stabilize the releases and make sure they work well. But it's taking longer than anticipated. I think a lot of the work that's happening on our CI infrastructure right now is going to help with that because it's getting a lot better. A lot of people have been putting a lot of time into that. The CI has been a perennial kind of problem for us, and they're really trying to get it right and make it work really well. And I think that's quite close. It's already a lot better, and it's quite close to working very well. And I think that will help a little with some of this. Otherwise, I'm not sure. There's a little bit of a downtrend here at the end of the graph, so maybe we're getting back to some slightly quicker releases. But this is what's been happening. And this happened. So we hit 10 years. Go check out this blog post if you haven't seen it. But yeah, this is in February. We hit our 10-year anniversary of the public release. And so, we've been at this for 10 years. I'm not sure what else to say, but I'm gonna end on that note. Please see this blog post. There are many nice remembrances and comments from many different Julia users. So that's it for this year. I will try to take some questions and thank you.
Thank you, Jeff. So maybe one quick question. Is 2.0 coming after 1.9? What can we expect from 2.0?
Well, after 1.9 will be 1.10.
Yes.
So there is no 2.0 plan. There's no date. There's no spec for it. There really is there's no such plan in the works. If anyone ever thinks of something that sounds like a good idea but would be breaking, we just tag it 2.0 as an issue and leave that for if and when that happens. But as for me personally, of the things that I would like to see, I don't believe any of them really require breaking changes. I think anything that I can see that I think we need to do can be done in 1.x in a not breaking way. So I don't see a need for 2.0 right now.
Thank you. And you answered this in your talk. Executables that one can just create. It's going to be probably still a little bit away, but it's actively worked on.
Yeah, it's just as Jeremy Howard said, that it's you know, he suspects there are things going on behind the scenes that are, you know, moving towards that, but it's not yet visible to someone who just says, you know, give me the one line I can run to get the executable. It hasn't reached that point yet, but the work is happening.
I'm looking forward to that. Okay. I don't see any questions right now. Thank you so much for giving the State of the Julia talk. I think it's something we're all looking forward to every year.
Thank you for all your work on JuliaCon. It's quite awesome.
Thank you. And with that, I will go over to giving the closing remarks on JuliaCon 2022. Looking over the conference, we had 3 days full of talks, roughly 124 lightning talks, 62 full talks, 14 experiences, 13 posters, and 7 Birds of the Feathers organized. Before the primary conference, we always have our workshop and mini symposia, and this year we had 15 workshops over 8 days. Roughly counting, we had about 8,000 online registrations, and as Jeff just mentioned, we amusingly also have about 8,000 packages. Just today, the Julia GitHub repository hit 40,000 GitHub stars. So this is a picture that I exported earlier today. It's a little bit fuzzy, but this is the amount of YouTube views we got over the conference, and the blue line is this year and the purple line is last year. So there's a little bit of a downward trend. I think that might actually just be that after 3 years of online conferences, people are a little bit tired of them. But generally speaking, we track in the same trajectory, and the video output is really one of the important things of JuliaCon, to showcase and highlight the diversity in the Julia ecosystem. This is one of my favorite slides. The upper side here are all of the submission we have received over the time since we opened the call for proposals on pre-talks up to the deadline. And one can see that we are a very just-in-time community. And so most of the submissions come in just before the deadline. Most of them come on the day of the deadline. And JuliaCon this year, as last year, was co-located with JumpDev. And so the breakdown in tracks was roughly, we had about 30 JumpDev talks and about 300-ish talks at JuliaCon submitted. Right, so now it is my pleasure to introduce Tim, who is going to present the Julia Community Prize. Tim, you're currently muted. And we can't hear you yet, sorry. Microphone is not yet working. No. Okay, so due to technical difficulties, I will present it. The community prize this year goes to the Documenter.gl team for their work over the many years on Documenter.gl, its ecosystem, and namely Morten, Michael, Frederick, and Mauro. The second community prize goes to Frames White for her many technical, social, and educational contributions across the Julia ecosystem. It is way too much. We couldn't list it all. And the third community prize this year goes to Shuhei Kadowaki for his work on chat.gl and his recent work on the Julia compiler and improvements. And Jeff highlighted them in the State of the Julia talk as well. The JuliaCon Community Prize is presented on behalf of Professor Alan Edelman, Professor Tim Hawley, and Curtis Vogt. On a personal note, we've been organizing for the last couple of years the JuliaCon proceedings, and I just wanted to remind everybody that any accepted speaker at JuliaCon is eligible to submit their work to the JuliaCon proceedings. If you want to learn more, there is an announcement on Discourse, and we also you can visit our website to find out how to submit. While you might think the conference is over, it is actually not. As usual, there is a hackathon on the weekend after JuliaCon, this Saturday and Sunday. It is going to happen on Discord and GatherTown, and see the hackathon channel on Discord for more details. There are going to be some volunteers are putting together topics that they are going to mentor, and if you're interested to work on any of that, just join. Try to coordinate with these volunteers and have a fantastic time at the hackathon. And now to the most important announcement. JuliaCon 2023 is hopefully going to happen in person. It is going to be hosted at MIT in Cambridge. And write down the dates right now. It's going to be between July 23rd to 28th. If you're interested in volunteering for JuliaCon, please reach out to the organizers at juliacon@julialand.org. And with that, I hope that you're going to enjoy the last half day of JuliaCon, that you're going to join us tomorrow for the hackathon, and that we see you next year. Thank you so much.